Hello, good afternoon, everyone. So today we are going to discuss about the basics of networking. Yep. So the first topic is we'll see what is OSI and TCP/IP model and the topologies and communication, and followed by that we'll see the functions of every protocol in every layer, and followed by that we'll see what is encapsulation overhead. We'll do a case study. And later, we'll do a lab for encapsulation overhead, and also we'll see in the EVNG, we'll see what is full duplex and what is half duplex, duplex mismatch, and what is link speed. Followed by that, we'll see what is MDIX, what is auto negotiation, cabling standards, NIC, the significant of MAC address, and difference between hub, switch, router, and firewall. And followed by that we'll see how ARP works in the lab, and how ARP works in the same subnet and how ARP works in a different subnet. And followed by that we'll see what is proxy ARP, what is gratuitous ARP. Followed by that we'll see the layer 2, how this Ethernet standard has been evolved over the years, and the structure of Ethernet 2. We'll see the Ethernet 2 header, and followed by that we'll see what is collision domain, what is CSMA CD state machine mechanism, and followed by that we'll see what is frame check sequence, cyclic redundancy check. It all comes into the layer 2 header, and we'll do a lab of Ethernet header packet analysis. We'll do it, and if we have time we'll cover up the IP addressing part. And with this, having said this, also, I'll tell you how to set up this EVNG lab, because that's the primary thing everybody should do it, right? So we learn stuff, and we are learning here. So along with that, practically it should be a parallel, right? So it should be practically, you should implement, and then you should do the lab. Only then you will get the results, and you will struggle somewhere, then the results may be, you will not get results sometimes, and you'll do a troubleshooting, you'll get into a problem. So that's how your actual learning starts. So I'll tell you how to set up a lab, and also we have a separate video. So our trainer, he did a video for a complete EVNG setup. So I'll give a link for it, and also I'll tell you how I build this lab using EVNG and the images. So let's first start with OSI and TCP/IP model. Let me open up the whiteboard. And let's go to the OSI. So the objective here is, here we'll discuss about the OSI model. Along with that, simultaneously we'll do a lab along with this. So we'll do like that, one topic at a time and followed by the lab. So you guys feel engaging and you can get it what exactly we are discussing. Yeah. So this is a quick comparison of OSI and TCP/IP model, and we know, right? I mean, we are all predominantly, not predominantly, I would say. I mean, right now we are using TCP/IP model, but however, the whole thing, it started and evolved from the OSI. So OSI is a Bible for TCP/IP. Even though if we are using a TCP/IP model, always it is good to compare your packets with OSI model. So why I said OSI is, I would say is OSI makes sense compared to TCP/IP. So once you get a fair understanding of how the whole all this layer interconnected and how they exchanges the payload packets and whatever it is, but if you understand the OSI reference model, then TCP/IP would be better. Anyways, we are using TCP/IP model, as I said, but for the understanding, every time if you look the packets from the OSI perspective, that gives you a more clarity and visibility. So let's start with this. So we all know the wire, right? So when you connect two devices, so here, example, here you got a device. It may be a router here, and there is a router over here. Let me erase this thing. Yeah. So pretty simple design for understanding here. So you got two routers that is interconnected like this, right? You have a cable going on. Sorry for the bad diagram here. One second, guys. Let me adjust my writing pad. So you have a connection running over like this. So imagine this is how it connected, right? So this particular part, right? This is your cable stuff, yeah. This is your cable running here. So this is called a physical layer. So everything is bits. We have no control over that. So how this is interconnected, we all know we use a different standards, a different cable standards. The traditional standards we use Cat5, Cat6 cable, Cat5, Cat5e. We call this as an Ethernet cable, right? So the Ethernet cable is connected between two devices. So everything is bits. So if you look at this, this is Cat5, Cat6, and sometimes if your distance is too long, example, if you're connecting if your enterprise is somewhere, you are in the Bangalore office, or you may be anywhere, yeah, from Bangalore to if you want to connect to a nearby location, maybe it may be 3-4 kilometers away, 2 kilometers away. So there is some specification with the optical fiber standards, but generally for the long distance, if the packet has to travel, it never ever travels in the Ethernet, and we know optical fibers are a long cable, and it runs and it connects at a far distance. So if those scenarios and if for those design implementations, they use optical fiber cable. And UTP is unshielded twisted pair. We call this cable standard again, comes into that. So basically, you have to understand about the optical cable, and the Cat5, Cat6 are most widely used, and we are now using Cat6 for interconnecting your firewall switches. And it depends. And if you want a higher throughput, sometimes they use optical cables. And even in the cabling, you have different options, right? In the cabling, you have multi-mode fiber. Just give me a minute. Yeah. So here we got a multi-mode fiber. Multi-mode fiber and single mode fiber. So for example, in your data center, if you have devices like this, devices like if you want to connect your router to a switch, and if it is an access device, an example I'm telling. So if you want to do an optical fiber cable, they use a different, modes of cables, right? So that's it can be a multi-mode fiber or single mode fiber. So that depends on the distance. So if the distance is less, and if it is just connected in the same rack, they'll be using a multi-mode fiber cables. So these are all the different types of cables that is traditionally used to interconnect the network appliances in the data center and the enterprise racks, right? So this is physical layer. So coming back to the data link layer. So here comes, right? So in the data link layer, this is all we call this as a frames. So exactly, we start inspecting the packet from data link layer. And if you see the most widely and the switches are used, right? The switches are used in the data link layer. And if a packet is coming in from the host here, if a packet is coming in from any computer or any PC here, if two computers are interconnected like this, yeah, LAN to LAN connection, this is a PC and this is also a PC over here. So what happens? The traffic has to actually go through the switch. It goes like this, right? So the packet goes through the frames goes through the switch. So in the layer 2, we should call this as a frames. So the frames is going through the switch, and the switch is going to populate its MAC address, right? We call it as a CAM table. We'll see that when we do that, we'll see that how exactly it learns the MAC address. So it doesn't care about anything else. It just look for the three key parameters. What are all the three key parameters we should remember for the data link layer? One is destination MAC address. Source MAC address, followed by that ether type. This is very important. Example, if this PC is going to send a ARP request, uh, there is a different Ethernet type stand. I'm sorry, the ether type is different for every protocol. The example for ARP, there is a value. So in the Wireshark, we'll see that why ether type is so important is because that gives insight of what is coming next. Is it this particular PC is trying to do an ARP, or it's trying to do just an IP communication, right? There is a difference between ARP and the IP communication. Yeah. ARP is something, the whole objective is find the destination MAC address. IP is IP to IP communication. So once I get the destination MAC address, only then my IP communication happens. Your packet forwarded from one place to another place here. From A to B, it's forwarded only if I know the MAC address. So ARP has to happen first, followed by the IP address. So even when you're troubleshooting your network, so you have to compare, is it if you connect a new host, are you really seeing the ARP request coming through a device? It can be a switch or a router, right? So you should apparently see your ether type header should be ARP. And from the there is, as I told you, there is ether types has a different value. For IP it's a different ether type value. For ARP it is a different ether type value. So based on that, you will actually figure out, okay, what is coming next, what is going to happen next. So that gives a complete insight about what's going to happen next, right? So if this is an ARP request, so the switch, once the computer does an ARP, the switch doesn't care about the ether type, but it knows, okay, this is an ARP request, and we know that it's an ARP request. So this is forwarded again to the upper layer that is called network layer. So we all know the network layer is the most predominant devices or the routers, right? This is your routers. And I hope you guys are all working in the enterprise in some kind of I mean you are working on the same networking domain, so you guys have definitely have a good understanding about what is routers and switches. And anyways, we'll discuss about that in detail. So here in the OSI reference model, so this is again a router. Why router is called as a layer 3 device? Because it doesn't care anything other than the IP communication, right? So all it looks for, let me erase this. So in the network layer, so imagine there is a router here and there is a router on the other side, right? So this is a host to host communication here, TCP IP. So we'll understand better. So here all it looks for inside the layer 3 header, it is going to just check source IP, destination IP. That's it, right? It doesn't look for anything else. But if your ARP happens in the layer 3, your ICMP and everything, this all the upper protocols that's being used, right? But it just look for, is it my header? It just looks for the source IP and destination IP. Other than that, everything is a payload for him, right? So all it focuses on source IP and destination IP. And when you peel off your actual layer 3 header, what are the other key parameters we should remember and we should look at? The very important field is TTL. So as we discussed earlier, TTL can be 255, 64, and 128. It depends on the operating system. Yep. So the other field. So what are the key fields here we should remember? So we should remember about source IP, destination IP, your TTL, and IP identification number. This is unique, right? So IP identification number. And what else we discussed, right? Source IP, destination IP, then your TTL. Did I miss anything? IP identification number, then your differentiated services we discussed, right? So if the particular packet is iOS, if a particular packet is QoS treated packet, example, if it is a voice packet, if you are prioritized something, you can see in the differentiated services, right? That is called as DF bit. We'll see that in the Wireshark. So the key values are source IP, destination IP, your TTL, your differentiated services, and IP fragmentation. That is very important, right? IP fragmentation. So when a particular packet which crosses 1,500 bytes, so because that is the standard MTU size for any transport, if you want to send your data, it cannot exceed 1,500 bytes. But definitely you are pumping a lot of traffic, maybe your media streams or you're downloading a file. So what happens exactly? So whatever you send here, the router on the other end, it defragments the packet, right? So here defragmentation happens. So here defragmentation happens here. So if you're sending, example, if you are sending something like 2,500 bytes, So how it will do a defragmentation? So it will just allow 1500 first, and then followed by that the other rest 1000 bytes, right? So this is called defragmentation. So your packet is defragmented in the destination, and it's going to send it back to the application here. Let me erase this. So that is the key protocols we should understand in the layer 3. And coming back to the transport layer. So what are the two protocols we use? TCP and UDP. So when we talk about TCP, everything is a segments. We know that. So how the segments is actually maintained? What is the segment mechanism the TCP is using it? So example, if you got a segment, maybe you got your 1500 bytes of data. So example, here there is a source and the destination in the other side, right? So what happens here? I got 1500 bytes, but it's going to segment the pack. So it's going to segment this packet, a big packet. It's going to segment. It's something like 20 bytes of data. So this guy, it's going to send a very first message is a SYN packet, right? For the SYN, it has to send a SYNAC back. So for this SYN, it has to send a SYNAC back. I think this diagram is not allowing me to do that here. Okay, let me jump again. Let's refresh this. Okay. So I'm waiting for SYNAC from this side, right? And for the SYNAC, again, the source has to send a ACK for the SYNAC, right? Acknowledgement. There is three-way handshake. So, okay, this happened. So what is next? So this is going to send a sequence number, right? So it's going to tuck the sequence number along with the packet. So now, example, this is 20 bytes of data, and I'm going to add the TCP itself. It's going to add a sequence number. Example, it's 20. So the identification would be 201. So with this whole information, it's going to push the packet here. So what happens here? The other side, the receiver side, it should send the acknowledgement back. So what is the acknowledgement? Okay, I received your 20 bytes plus 1. So you can send it back the other sequence of packet. So the next sequence number would be 202. So for my sequence 201, I got an acknowledgement 201 here, over here, right? This is acknowledgement. So again, this sequence, it becomes a sequence number 202. Again, my packet is again divided again with 20 bytes. This is the first packet, and this is my second packet with 20 bytes. My sequence number would be 203 now. So again, now it's going to send this, right? Over here. So this is sequence number 202 from the source. So what is the expectation here? I should receive an acknowledgement for 202, right? So this guy is going to send an acknowledgement for 202 acknowledgement. So once I receive an acknowledgement again, okay, I got an acknowledgement for 202 ACK. I got it. So followed by that next, okay, let me put the sequence number 204 and send it again. So why it is doing this? Example, okay, if I send 201 and I got an acknowledgement, I sent it 202 and I didn't get an acknowledgement. So based on this, okay, I didn't receive an acknowledgement for 202, so I am going to resend this packet again. Let me delete this. Something happened with this. Okay, so let's take a new whiteboard. So we understood that, right? The whole process we understood. So here we are just talking about the acknowledgement now. So I didn't receive an acknowledgement for 202 from the destination. This is a source and this is the destination. Yeah, guys, please mute. I think I have to. Yep. So I didn't get an acknowledgement for 202. So it's going to resend this packet again. Going to resend this. So this mechanism, the TCP is using it to send it. So we discussed this earlier. So what is the, how why this is managing this mechanism? Because example, if I send couple of sequences, this is sequence number 201 and this is sequence number 202 and this is sequence number 203 and this is sequence number 204 and everything is stuck with the actual payload of 20 bytes of data. 20 bytes here and 20 bytes here. So what if I didn't receive an acknowledgement for this 203? No acknowledgement. So using the selective acknowledgement, TCP has a parameter called a selective acknowledgement. Using that, it's going to resend only the 203 sequence again. This part of data, not everything. It's going to send this back again to the destination. This is source and this is destination. So that is the use of selective acknowledgement. Let's jump back again to the OSI model. Okay, so we covered TCP and we know this three-way handshake and why it is managing the selective acknowledgements. And there are other parameters used in the TCP. So the most important parameters, and we should remember about TCP, is followed by this. As I told you, we have to look for your 4-tuple connection. That's the primary, right? So 4-tuple connection. So that is your source IP, source port, destination IP, destination port, 4-tuple connection. Along with that, it's using a sequence number and acknowledgement number. We discussed what is the use of it. Then followed by that, it is using MSS, maximum segment size. Yeah. And followed by that, it is using a selective acknowledgement, because if something happened in the middle and if some part of your sequences are missing, so only those segments will be pushed back again to the destination. Yeah. So these are all the key parameters there. So when we dig deeper, you will see the other options like window scaling, what is the buffer, TCP flags. Yeah, we'll discuss about every single flag. So these are all the key values there. So when your communication actually happens, you have to first look into your flags, TCP flags. So let me go to a different presentation for it. So we are using all this 1, 2, 3, 4, 5, 6 flags, right? So we all know in the 3-way handshake, it uses a SYN flag, ACK. Only we are using SYN, SYNAC, ACK. So we are using only these 2 flags in your 3-way handshake. This is primary. If your 3-way handshake is not happening, then your 4-tuple connection is not happening. So the firewall, the traditional firewalls before the next generation firewall, that's completely, we make use of this firewall using this TCP 4-tuple connection, right? Because we define the source IP, we use the source port, destination IP, and destination port. Only based on this, we block the traffic. Yeah. But with next generation firewall, okay, this port is allowed for what application that come, then again, that's we are doing a layer 7 inspection now. So that is very important. Your 3-way handshake and 4-tuple connection is a very key and primary understanding you should have to understand the other parameters of TCP. And followed by that, we have a flag called push flag that indicates that the receiver should push the data to the application layer as soon as it is received. Example, if you have a telnet connection established here, it can be anything, right? If you try to do a telnet to this particular device, so always if you look at the QoS mechanism, your packets, We call this as first in, first out, FIFO. So example, your telnet traffic is waiting in the queue. This is a lost packet, 3, 2, 1. Then there are some communication is happening. It's in the buffer flow. And this is the, this is waiting, and this is the third guy waiting in the queue. But still, if your push flag is, we'll do that in the lab now. If you established a connection, and if you want to push this, and it has to given the priority, but it will wait. Yeah, it will wait, but this take the precedence over the other packet. So it will push out this 2 and 1. It has to wait, but this is forwarded pushed before 2 and 1. So that is called, this indicates the receiver should push the data to the application layer as soon as it is received. It is expecting that the receiver should send this back, the information what. So if I open a telnet session, I should get a response back. So reset indicates that the connection should be reset, because we discussed this yesterday. Yeah. So it's TCP, is a peer-to-peer communication here. So again, a 4-tuple, source IP, destination IP, source port, destination port. As I told you here, the destination port 443 is blocked locally. So when I am trying to establish a connection, this guy is going to send me the reset packet, right? The destination is going to send a reset packet. Because my port is closed and you cannot establish a connection. There in the flag, you will see the reset. So who is sending a reset? That is important. So, okay, this guy is resetting the connection. So it can be a local device, or there will be a firewall, or any device that's something blocking in the middle. So that is the use of reset. And urgent pointer. So when it is used, I'll show you the use case for those. You'll understand better. So here, push flag indicates that the receiver should push. The receiver, yeah, not the source. So the communication is happening between these two devices, and it is expecting the receiver. Here, this guy is the receiver. He is the sender. So the application layer, as soon as it is received, without waiting for more data to arrive, this flag is often used in real-time applications such as your voice and video streaming, where a delay in the data transmission can result in poor user experience. When push flag is set, the receiver pushes the data to the application layer as soon as it received, even if the buffer is not full. This reduces the latency that ensures the data is delivered as quickly as possible. Yeah. So the whole point is we are waiting for the receiver to push this traffic. This reduces the latency. So the urgent flag indicates by the name, that's very urgent, and it's not going to look for anything else. It just sends a packet. It never waits for your queue. It takes the precedence over all the packets waiting in the queue. When the urge flag is set, the receiver knows that it should process the urgent data first before processing the rest of the data. So example here, it got a telnet request and it got an HTTPS request. But as per the priority, it has to give a precedence to HTTP. But since it's set with the urgent pointer from the source, the destination, the receiver has to send it back quickly, because when the urgent flag is set, the receiver knows that it should process the urgent data first. The receiver should know, because the sender sent with an urge pointer. This is useful in situations where certain data requires immediate attention, such as control signals or error messages. So here, an example. For example, when a user enters a URL in a browser, the browser sends a request to the server using the TCP protocol, and we all know that the header. If you open up the HTTP header, you should see if user is expecting something from the destination server, because the whole thing is HTML code in the destination, and it's going to send the HTTP GET request. So this indicates that the HTTP GET request requires an immediate attention. Yeah. The request is divided in two packets, and the urge flag is set in the packet that contains the HTTP GET request. So urge flag is used when certain data requires immediate attention. This is useful in situations where control signals or error messages needs to be processed immediately. So this depends on, we have no control about this. Is all the application specific, right? So it is all purely how this application is designed and how it works. If there are 4 applications and this is all predefined, right? So that particular application, if example, as I said, if your talent application is a priority, so that's take the precedence over the other packet. So here the precedence goes for the precedence goes for the HTTP request here. So that's how the TCP flags works. Just a minute. So we discussed about OSI model and we are going through that. So coming back again to the OSI reference model here. The session layer. Yeah. So where session layer is used, you are tunneling. Okay, so let's go back again to a new whiteboard. That would be helpful. No more space to write. The very best example would be very simple. You have your PC, you opened your web browser, you open multiple tabs with multiple websites here. This is website 1, this is website 2, and this is website 3. So you're trying to talk to the internet. So what happens here? So for website 1, you started a session. Website 2, you started a session. So when you opened this tab in this particular website, it's going to log when you log in and when you log out. It's one typical example for session. So like this, every session, everything is managed by this, the session layer. We have no control over that. And in your tunnels, when you established your tunnel between the devices here, so when you break your tunnel, if something happens and disconnection happens and everything is monitored and managed by the session layer. Because we are not going to do any inspection with the session layer level, but we have to understand where it is being used. So if you are using a voice traffic in your SIP, when you initiated a call from the source to destination, when the disconnection happens, so gracefully both sides they hang out the call. Yep, those sessions are managed by that. And apart from that, if you open your RPC, RPC is your remote procedure call, right? When you open your RDP connection, when you log in and when you close your connection, everything is managed by session layer. When you open your RDP, you will type your username and password. That's the moment when you log in, so that locks the session. And when you close the session, so it maintains and manages the sessions based on your RPC protocol, right? That's remote procedure call. And presentation layer. Yep. compression and encryption protocol. So why we say that? Because if you look at in the website, in any website, right? We take this empty website here. Yep, I mean, yep. If you open a website, you know that everything is programmed in the back end. We don't know anything what's happening there. But everything, it's a programmatically they are designed, the UI, the functions, and everything is managed, right? So the whole thing is managed by the presentation layer. Example, if you open a website and if you see images, but there is actually a program code that's running in the background to display into the human readable format, right? So those things are managed by the presentation layer. And the final layer is your application layer. So we all know this, right? So we use a DNS, we use HTTP. Yeah. Here in your web browser, if you open a HTTP request here, and yeah, let's go back to the whiteboard. Let's quickly finish this. Okay. So when you open your browser, even this is an interview question, right? Happening. Title must be why it's adding a title to this. Let me open this. Definitely something wrong with this whiteboard. Okay, so let me open up Paint. Let me open up this Epic Pen. Yeah, application layer, right? So this is a computer. One minute, guys. Actually, something wrong with the computer. So this is an application layer, right? So we know multiple application protocols. Example, HTTP or DNS. Even in the interview, they ask us, right? So when you do, what is the very first packet that goes from your computer when you try to access a website, something like google.com, or it can be your microsoft.com. The very first packet is your DNS packet, right? For this DNS request, I should receive a DNS response. So what exactly it is? So I'm looking for someone, a resolver, to give an IP address for google.com because I don't know the IP address of google.com. So in the DNS request, all I'm requesting is an IP address for this URL because we know we cannot remember every single IP address in the internet. Yeah. So when we try to browse a website, so when the DNS request goes in, the DNS resolver at the who has an IP address for that, he's going to respond with, okay, here you go, the IP address of the Google server is 8.8.8. So for that, we are using a DNS, right? So your first protocol that kicks in when it goes out of your computer, that's your DNS request. So one after that, I get the IP address of it, right? So then your actual network layer protocol works, right? Your IP packets will be exchanged. IP communication happens here. So this is how every every layer works together. Once got an IP address, so what happens here? Then the network layer is going to check, okay, what is my source IP address and what is the destination IP address? Only that. So other than that, what it does. So example, I got, so my source IP is 10.0.0.1 here, and the destination is 8.8.8.8. And my source MAC address is A.B.C, example, my MAC, my IP. But to reach over there, I need the destination MAC address. So that's how the ARP kicks in, right? It's going to send an ARP request to whom? Because this is totally in a different subnet. So what happens here? I don't know the destination MAC address, but I know the destination IP address. So let me erase this now. So imagine you got a router here, you got a switch. So you have VLAN 10 and VLAN 20 here, and you connect it to your internet cloud. It's your internet. So multiple hops, right? That connects. They do all this BGP peering. BGP is running. Example, there after multiple hop, there is a switch. Here the actual Google server is connected with an IP address 8.8.8. So as we know, we said we have source IP. You got your source port, destination IP, destination port. So TCP got all the information here. So for TCP, no problem. Agreed? Because all it looks for source IP, source port, destination IP, and destination port. It doesn't care about the MAC address. Only for forwarding, the switch will do the forwarding based on the layer 2 header. So here, so what router is going to do now? That's the, that it got a protocol called ARP. So it's going to send an ARP request. So we know ARP is a broadcast. What is that? So all is 255. In the layer 3. And in the layer 2, all are S. So this is a layer 2 broadcast. And this is a layer 3 broadcast. So what is the meaning of this? So this computer over here on VLAN 20, that's assigned with 20 003, and here the gateway is configured 20001. And you got multiple computer over here. So this guy is going to send an ARP request. So every single port. So this ARP request goes through the switch and it learns this MAC address, right? The MAC address of over here. Change the color to differentiate. Source MAC and the destination MAC. So it sends a broadcast to everyone. That is broadcast. Broadcast. This is going to send a broadcast. And also this VLAN 20, right? So configured here VLAN 20, it receives this broadcast. Yep. And then this switch is going to check, okay, my default route points to this router and I don't know about the destination MAC address of this. The switch doesn't have a destination MAC address for this because that is not in the local LAN, right? So what happens here? Again, now the switch do a ARP request again because that's not in my routing table. So that hits in every single port. And this router is going to say, okay, you received this. Even I don't know where is it, but can you send this back to my gateway over here? So once this receives, yeah. So we all understood until this point. So the router over here, it received the packet now. This is a switch. This is connected to internet. It's going to look into the routing table and I don't know the destination. The destination is something 8.8.8, but I have a default route pointing to the internet, right? All zeros. Example, a public IP address of something like 5.6.7, sorry, 5.5.5.5. An example. This is the next hop here. So this is going to send an ARP request again here. So this goes right until the ARP request keep on going over the internet again and again and again until it finds. So example, this is here is your actual Google server is connected over here. So it comes here, then finally it does an ARP request, and this particular switch with this IP subnet 8.8.8.0/24, this is going to respond back, okay, I know about the MAC address of this, what you're looking for, because that is in my local LAN. So that's how your whole packet flow across the network. So that's how the data packet goes from one place to another place. The everything is happening with ARP. Without ARP, you cannot do anything. Yeah, now let's jump to the lab now. Where is my lab? Just give me 1 minute. Let me on my lab 29. Some admin event G Eve. So yeah. Let me try to open this. Okay, let's see what is the first protocol we'll check. We'll go through OSI, we'll go through every packet flow. Okay. Show IP interface brief. Let me check my connection. I can do a ping to 10.0.0.1. I give show IP ARP. I can see the here MAC address of this. Okay, cool. So very first topic we are going to discuss about the OSI model, right? Okay. Let's go by layer. How OSI actually happens here, yeah, with Wireshark. So let me close all this packet, all the captures. I want to close everything. Okay. So let me go into start the capture. So for that, you have to right click, go to capture, and Ethernet 0/1 is going to Ethernet 0/1 on the other side remote port. So I have to run a capture here. Okay. The capture started. So now the first we'll see the Ethernet frame and the layer 3 and layer 2. Can I see my ping packets over there? I think it should take some time. Why I cannot see my ping packets? Okay, let me try from router 2 to router 1. Yeah. So what happens here? I'm trying to capture the traffic coming into Ethernet 0/1. Ping 10.0.0.1. I can ping. Okay, now I see packet coming in. Okay. So let's take this capture. Let's stop this. Okay. So let's come from Ethernet 2. So what happens here? So this computer from this R2 to R1. So let's take from R2 to R1. Right over here. So this is the MAC address, right? Source MAC address is 2010. We'll just focus only on last 4 values. But this is a complete MAC address. Yeah, but we'll focus on 2010 for easy remembrance. Yeah. So let's jump back. Let me see. Show IP interface brief. Show interface Ethernet 0/1. It is 2010, right? If you see, this is 2010. And the destination is coming to where? Show IP interface brief. Ethernet 0/1 is assigned to 10.0.0.1. If you look at the diagram, you'll understand. So this is, we are talking about this. We just checked this, and this is my source port, and this is my destination port. Yeah. Let me check this. Show interface Ethernet 0/1, and this is 1010. So this is 1010, my computer here. So this is 10.0.0.2 and this is 10.0.0.1. This is router 2 and this is router 1. Then followed by that, what are the key values? So what is this 0x0? I told you, right? This is ether type. So 0x0800, Let me show you a document for it. I put something over here. I want to add a text. Let me make it a little bigger. Oh. So the ether type of IPv4, I don't think you guys can see this, right? Let me delete this. So let me increase the font size to 18. Okay, the ether type of IPv4 is 0x0800. So you see that here, right? The capture, you see the ether type over here. So it says that this is an IP packet and this is for IPv4. We are using an IPv4 here, right? This is for IPv4. Yeah. So that is very important field, as I said. Okay, so the computer is trying to send an IP communication. Yeah, the layer 2 confirms this because you are doing from the wire, so it detects, okay, what is then my next protocol, that is IPv4, but this is not handled by the switch, but now the IP communication is happening there. There are different ether type values. Let me give you the different type of ether types. Let me take the document here. What is the ether type for IPv6? Let me copy this, go back. I can't do this. Cannot do. Okay. Something happened, freezed. So if the payload contains, for IPv6, the ether type is 0x86DD. For I4, for IPv4, it is 0x0800. Right? In the Wireshark, we saw that. Hi guys, you guys can hear me? I gave an unmute permission just to check. You guys can hear me?
Yes, we can hear you.
Yes.
Yes.
Okay. I mean, I thought the screen is
Yes.
freezed. Yeah. Thank you. Yeah. Let me mute you all. Something crazy is happening this computer. So these are all the different type of ether types. So here we see this is an ether type for 0x00, and the communication is happening only for IPv4. So that's the whole point. Yeah. So then if you look at this, we discussed about this. So the total header length is 20 bytes. And I'm using any kind of QoS. No, the IP is not marked with any kind of DHCP value, because in layer 3 everything is DHCP. And if you actually using anything with a layer 2 QoS, it should be marked with COS, class of service. And DHCP stands for differentiated services. Yeah. If you see this differentiated services, we call this DSCP here, over here. So the total header length is 20 bytes given for this. And if you look at this, the source is coming from 10.0.0.2 and the destination is 10.0.0.1. If you look at this TTL is 255. We'll add one more hop and we'll see if the TTL is decrementing here. Let's go back here. Let me add one more device. So let me turn on this switch. So IP interface brief, config. So it's Ethernet 0/2 over here. So first thing I have to do a no shut, exit, interface Ethernet 0/2, IP address. So this is a layer 3 switch, and you have to give no switch port command to make it as an IP port. So IP address, now I can give an IP address. Let me give 12.0.2, 255.0.0.0. Yeah. And if I go to R2, if I give show IP interface brief, include assigned, configure, and interface Ethernet 0/0. This goes to Ethernet 0/0 goes to R6. So let me rename this host to switch. So R2 goes to the switch, and the interface Ethernet 0/0 and IP address 12.0.1. 255, 255, 255.0. I think I gave the same thing over here, right? No switch port and gave, okay, 255.0.0.0. Okay. Let me change the subnet mask to 255.0.0.0. Okay, I did that. If I give show IP ARP from R2 only, I can see this, right? Show IP interface brief. This is admin down here. If you look at this is admin down, so no traffic is going over here. So let me start the capture. to see what's happening in this router when we do this. Okay. So what is that? Ethernet 0/0. I should see traffic because that port is down, so I don't see any traffic over here. So Ethernet 0/0, no shut. I see traffic coming in. You can see this gracious arc. We have that here, right? Okay. So what it is telling, gracious ARP, it tells that, so if you look at this for everyone, right, target is everyone. So for everyone in my network, example, if I quickly jump back here, it is telling that, but this happens only to where, if you look at this, that's why we have to understand. So the sender MAC is this, where is it? The center MAC is source is what, 12.0.0.1. If you go to 12.0.0.1, but in the logs, it can be any vendor. You cannot see this here, right? Sure. If you give show log, you don't see any kind of messages like this. This is very helpful to detect your duplicate IP address. Yeah, we'll try that. Yeah. So, so IP interface brief. And what is the source IP? 12.0.0.1, right? So if you go to show interface 0/0, and you see this MAC address, right? 20 yeah. It's telling that for everyone, it is telling hi everybody for the layer 2, right? For everything in the layer 2 is a broadcast, and it happens only for your local area network, right? So it's telling that example. Okay, let's take this as a switch, and this all the computers connected like this. So let's take very simple topology. So let's say you got 3 PCs over here, PC1, PC2, and this is PC3. So it is a broadcast to everyone. This PC sends a broadcast to layer 2, all F, to all MAC address in the same LAN. Example, this all in VLAN 10. This is in VLAN 10 and this is in VLAN 10. So everybody receives this, and this PC is telling that my computer is 12.0.0.1. So here we got a router, but the ideology is same. So that is called gracious ARP. So why it is doing that? Because nobody else should use this IP address, because I have assigned with this IP address in the local LAN. What if somebody assigns this IP address? So if we look at, okay, so we'll do that. We will do that in some time. Yeah, but let's finish this Ethernet headers. So what else I should see here? I don't see any IP packet coming back. The capture. What do I see apart from gracious harp? So we understood, right? So in Ethernet, we use typically the three parameters: the ether types, source MAC, destination MAC. In the IP field, we use source IP, destination IP, and TTL. So we said we now we are going to add one more device here, and let's see if TTL is decrementing or not, to see my routing works. Yeah, that's the whole objective. So let's jump back to that. So To make it simple, show IP interface brief. From here, enable, what is the IP address of this? 12.0.0.2, right? I try to ping 12.0.0.2. I cannot ping. And what is the capture here? Let me close this. So because we have to run a capture only on R1. So let me do it again. This traffic is going over Ethernet 0/1, right? Show IP interface brief Ethernet 0/1. So let me run a capture. Go here, Ethernet 0/1, open the capture, let it run. And now we are going to do a ping. Just to see, I can inspect the packets in Wireshark. When I do this, but actually in the other end, if we do, we see the ping request, not here, right? Okay. Okay, fine. So let's establish a connection first. Yeah. Show CDP neighbor. So router 2 is connected on Ethernet 0. I bring it down. It's connected to Ethernet 0/1 and it's connected on Ethernet 0/1. But if I give show IP route, I mean, this router should know, right? If it tries the, so what happens here? So it's trying to send an ARP request for this guy 20001. Yeah, but since I don't have a route to 20001 here, no, it should be in the routing table, right? That's the key thing. Only then I can send an ARP. So now the packet is dying inside my router because I don't know how to reach to 12001. So what I'm going to do here, so I'm going to show my R table and it is 10002. So the other end connected over here, it is 10002. So let me make it very simple. So let me go configure. I'm going to do a manual route. So if I want to reach 12001, and what is the subnet mask for us? Show IP interface brief. I give show run interface Ethernet 0/0, and this is the subnet mask value, right? Sorry, and followed by the gateway. So if I want to reach 12001 and my Ethernet 0/1, I am connected to this, right? I am connected to 10002 and I'm trying to reach 12001. So I have to go, my packet has to go from here to this interface, and then I can jump in back to this interface where it is assigned 12, right? This goes here. Okay. So R1 coming back to the CLI, it's 10001. Okay. Because if I want to be specific, I should not use this because I'm doing for not for the whole network, I'm doing for a single address, right? So it should be 255, 255, 255. Yeah, because only one specific IP address. We all know this, right? So 10001. Okay, good. 10002. Show APR. So again, we'll try. Can I reach 12001? Yep, I can reach 12001. So where is my capture now? Okay, so let's do one more time. So here, what should we expect is an ARP. So to flush your R, actually it's in the production you shouldn't do that, but it's actually you have to go to the interface and you have to shut the interface and do a no shut. And let's see if I still see the R. Show IP R till I can see it, right? So if I do a ping to 12.0.0.1, ARP is not flashing out here. Okay, so what is my destination IP address here? Show run include IP route. So I get a gracious ARP, and if you actually see this, right, I flushed, and if you look at this, in my routing table, my next hop is 10.0.0.2, but I don't know the destination MAC address. This router doesn't know the destination MAC address. So what happens here? The ARP request, it is telling that my source IP is this, and the destination MAC address, if you see, all F. But I know the destination IP address. If you see the ARP, this is the ARP headers, right? So it is telling we are using IPv4 address, and we are using the source MAC address is this one. This is my router, right? So source IP is 10.0.0.1, but I don't know how to reach 10.0.0.2. Can you give me the MAC address of it? Apparently, I should see the ARP response back. Let me just do ARP. Yeah. If you see this, okay, I'll also explain. So if you just put an ARP, that shows only your ARP packets and that filters out all the other protocols. So from my PC, my router, it's asking for where is 10.0.0.2, and it is asking for 10.0.0.1, this next hop device, right over here, this guy. This is 10.0.0.1 and this is 10.0.0.2, and it's asking for the gateway, this egress port. Do you know how to reach there? Because 10.0.0.2 falls into my routing table, right? I give show IP route. So I know 10 network, right? But I don't know how to reach there, but I don't know the MAC address of it. Can you help me out? So since our next hop is 10.0.0.2 for 12, right? We are trying to reach 12. And but to reach 12, first I have to reach 10.0.0.2. So now it sent an ARP request and tell me who has 10.0.0.2, and it's asking my egress port 10.0.0.1 local router. And it is telling, see, the sender MAC is my computer. The sender IP, sorry, this is from R2, right? If you go and check R2, this guy, right? 10.0.0.2. Show interface. If you give this show interface command, you will see the MAC address of this 2010. So this guy is telling that this is my MAC address, 2010 source, and the destination is where? Comes to R1, right? Show IP interface brief. Show interface. Let me see 1010. So to this guy, to R1, it is telling, okay, you have to go there, and what is the information? So you are looking for the target MAC address, this guy. This is my MAC address. Here you go, you take it. So I got an ARP reply back. So what happens if you run again a ARP request back here? If you do a capture over here, if you do a capture over here in R2, because it is in the same routing table here. So it's just again it does an ARP request, but since it's in the local device, 12.0.0.1 is within this. If you go and check the routing table, you see this here. So this is R2, and if you see show IP ARP, and this guy know about this, right? It got the ARP table, I know it got it because it is local to this device, so it reached here. And let's see one more thing. I'm expecting one more thing to see here in my ping. IPv4, still this is one hop away, right? So I don't see it is decrementing. This is from 10.0.0.1 and okay, 12.0.0.1, right? You see, even here the TTL is not reducing here. Okay. So let me create one more device here. Let me add one more device. So coming to R6, right? Let's jump back to R6. So IP interface brief 12.0.0.2. So if I do a ping to 12.0.0.2, I cannot reach because I don't have a static route for it, right? Show run include IP route. It's 12.0.0.1. Okay, let's try now. IP route. Let's give 12.0.0.2. Same next hop. Why? Because I don't have a return route here. So if you see, show IP route, my routing table, I know 12, but I don't know where is 10 network. So if I want to reach this guy, 10 network, so IP interface brief, config IP route 12.0.0, sorry, if I want to go to 10 network, here, I want to go to 12.0.0.1, right? 255.0.0.0, the subnet mask of 10 network, and the next hop would be 12.0.0.1. So IP route, if I ping 10.0.0.1, I can ping where is 10.0.0.1. Show IP interface brief. Show IP interface brief. Okay, here is okay. So let me take a capture over here. If I send any ICMP reply back to 12.0.0.2. Okay. Let me do again. Let me do a capture over here. I should see the TTL decrementing. No, let me do a capture for Ethernet /2. Open it. Okay. So if I do a ping to 12.0.0.2, it shouldn't be okay. Let me go to okay. Here we go. Why it's not happening here? Okay, so let's stop this capture. So 10.0.0.1 is replying that if I want to reach you, you're just one hop away because you reach to this router, right? And it got the routing table here. Something happening here. Okay. So this guy here, if I take a capture here, same, where if you look at this capture, I see the TTL is decrementing here. That's a whole expectation here. Because from 10.01, if I want to reach 12.0.0.2, right? So that is, if I reach here, where is it? So how exactly the TTL works? So this host, it's going to put a TTL of 1, and it tried to reach over here. I mean, my screen is really got stuck. Guys, you can hear me, right?
Yes, we can.
Yes, sir. Yes, sir.
Yes.
Okay. Something, I think, some disconnection or something is happening. It's not responding now. Okay, so you can see here, right? So from this router, it reaches here if with a TTL value of 255. Once it goes here, it decrements the TTL to 0 and it sends it back again. So this router thinks that, okay, so it is just one hop away. Why I see only one hop away here? Because in the R2 routing table, if you look at the R2 routing table, show IP route, I know where is 12 network. If this device doesn't know where is this 12 network, so once I receive this, it may think, okay, I cannot reach this, so I have to put the TTL value of 2 over here, and I have to send the TTL again to find this, and it cannot reach with 1. It comes back again, it puts a 2, and it will send this here, it decrement by 1, and it will send again to this device, and it finds here. So since this is just one hop away, because this router has a routing table here to reach in, how it knows. So it's not traversing any other device here. So until it finds the destination, the TTL keep decrementing. So here we see the TTL is decrementing to 254. Okay, so guys, I mean, you can ask your question based on this. I mean, we are going very long, and if you feel like if you have any questions, maybe just 5 minutes. Yeah, then we'll followed by that we'll start another topic. So far, you guys are understanding. I mean, you guys can understand what is layer 2 and what are the key parameters of layer 2 and layer 3. So what is your viewpoint about this? I gave a unmute permission for everyone, right?
Yeah. Hello, sir. Sudha.
Yeah. Yeah, I can hear you. Hello? You guys can hear me?
Yes, we can hear you. So far, I don't have any question, Praveen.
Mm-hmm. Cool.
Yes, sir. Actually, it was muted. So I am having the doubt in selective acknowledgement. So who sends the selective acknowledgement, the receiver or the sender? And what all information it shares with selective acknowledgement? Is there any payload, sequence number, or something else?
Yeah, I mean, right now today, yeah, I mean, we haven't touched that, right? So I'll take, we will do the capture and definitely see that, but because now we will divert from this topic, right?
Oh,
Definitely, I'll answer this question because we haven't started the selective acknowledgements. I mean, that is just I'm going through the, yeah, just giving a glimpse about TCP. We haven't discussed because TCP, if you look at this four topics, we have, where is TCP comes here. We haven't started TCP. We are just doing the OSI now. Just layer 2 and layer 3, right? We haven't touched the layer 4 TCP.
okay. Okay.
We'll go by layer. Yeah. Yeah.
Okay.
Thank you. Yeah.
Hi,
Any
Pudun sir.
questions
Yeah.
related to this? Yeah.
So there was just a query like push flag. Like you said, the SSH and telnet will be with the push flag. But
Mm-hmm.
when client want to access the server, it is done immediately. So does it not urgent? I'm a bit confused.
Yeah, I will show you. I mean, when
Mhm.
I'll generate the push flag, yeah, you'll
Mhm.
understand. But related to this, if you have any questions, I mean, push is something we are going to do next.
Okay, so does this SSH telnet is the example of a push flag, or is it with urgent? Because generally it is asked in the
No,
interviews
that
and
is
all that.
for a telnet, it is push,
Okay,
not a gen flag. Yeah.
okay, okay. And what is the example of urgent flag, if I can say?
Urgent flag, if you see, that's used for voice streams and video streams, but I don't think we can generate a traffic for it, but we can analyze
Okay,
those PCAP. We'll download
okay,
the PCAPs and we'll analyze the voice streams and we'll see the urgent flag and who is sending that generally.
okay,
But the urgent flag is something, the source sends this is bit urgent and the receiver has to respond back for it.
okay. And this telnet and SSH, they all are come under the push flag, right?
Push flag. Yeah.
Okay, so
HTTP is predominantly used for urgent flag.
HTTP, okay.
HTTP get and post. Yeah.
And when there is a push, in that case, the TCP, the data will like stored in a TCP buffer, right?
Uh, 1 minute. I'm really happy to answer your questions.
Okay,
And what's your name? It's Indu, right?
right.
But Indu, only to this will ask questions. Otherwise, that's
Okay,
completely diverted, right? Because other people they don't know what is TCP. But definitely, I'll keep this in mind, and you remind me, and definitely I will answer that because we'll go through everything like this. The whole objective is we are going every layer, right? So
okay,
layer 2, layer 3. We'll just
okay. So
talk about layer 2,
TCP
layer
we
3
are
now.
doing later.
Yeah. I mean,
Okay,
not later here in the topic. We just touched layer 2 and layer
okay,
3 now. We are just doing a layer 2 and layer 3 and what we see
okay,
there. Yeah.
okay,
The
uh,
encapsulation, decapsulation, that's something we are discussing now. Yeah.
okay, okay. Understood.
Yeah.
Excuse me,
No
sir.
problem.
Here, Ali here. Trying to ask you regarding ARP.
Uh-huh.
Can you give some use case for an issue in the environment about ARP? Let's say we have a PC trying to send a switch, and there is a router and there is a firewall. Okay.
Mm-hmm.
Let's say I have there is two peer, and I need to send to the other destination. Destination, it's in different subnet. Okay.
Mm-hmm.
So a user asked me, I'm a firewall administrator, and he's telling me
Mm-hmm.
that he cannot reach to the destination. So in my case, I will ask for source and destination.
Mm-hmm.
Okay, I will generate traffic,
Mm-hmm.
and I will see if it's allowed by the firewall or not. So in this case, let's say there is an ARP issue. So how I came to know there's an issue, like an ARP issue in this case. You understand me?
Yeah, I understand. So the whole fundamental of ARP is to find the destination, right? So I don't think they have a rule. Okay, if you say you may check, is there any specific policies to block the complete traffic for it? You're blocking the whole IP communication to it, then your ARP request never have cross or it doesn't go through your firewall, right? Because if you're blocking the destination, if there is any ACLs, if you try to block, then your ARP cannot, I mean,
Let's
the
say that
firewall
let's
cannot do an ARP for that particular destination, right? But it can do a ARP, but you will not receive an ARP reply back. But that's again the whole IP communication that we are blocking here, right? If there is a firewall.
yeah.
But if it is allowed, and if you're asking, can you rephrase your question? What is the exact question you asked?
Okay, let's say policies are allowed, already allowed.
Mm-hmm.
But in some case there is, let's say, because one issue happened before, I don't know, with my colleague,
Mm-hmm.
and he was troubleshooting, and he was saying he was checking with the network team,
Mm-hmm.
people who's managing the router and switching,
Mm-hmm.
and he was telling them if there is ARP request or ARP reply
Mm-hmm.
in that time. So in this case, in what case I should check if there is ARP request or ARP reply? ARP reply.
Mm-hmm. So
You
okay,
understand?
so yeah, I understood. But see, very simple. So instead of ARP, you know how this routing table works, right? So if you give show IPsef, we have to understand a bit about this. So there are two key factors that is happening inside the router before the ARP. Example, let me take my pen here. So you got your PC or maybe any source, and this is your destination, and this is source, right? And this is your destination here. Over here is your destination. So you got a computer here. So when this guy sends an ARP request, so apparently here, if it is, you are telling that it is a different network. So this is a 10 network, and this is a 20 network. Yep. So for this ARP request, because it's going to check, is it 20 is in my network. So it is configured in the remote device here, for an example. So the ARP request comes over here. Then again, this router is going to do an ARP request because it's going to check inside the routing table, right? So example, if you're going to check inside the routing table, and if I don't have, so routing table, you know, for if you're running multiple routing protocols, you'll come to know for every protocol there is a routing table. If you give show IP route, okay, it got stuck. Show IP route BGP. I'm not running BGP here. So I show IP route OSPF. I'm not running an OSPF here. So the best route will be placed there. Example, if I know the destination with two different, where it's gone. So if I know the destination, you can still hear me, right?
Yes, I hear.
I don't know this diagram where it went. So example here, if I'm trying to reach a destination of 20003, so this two routers, right? So this is 20.0.0 and this is 10.0.0. So I send an ARP because it's not belonging to my network here. This ARP request. So who has to send the ARP response back? This guy, right? ARP response back. So what I'm telling is, okay, this particular destination, if you know this network with BGP, and you know about this network through static route. So this is a routing table for static route. And this is a routing table for BGP. So I know about 10 network using two routing protocols, but in the routing table, in the actual routing table, this is called RIB, right? Routing information base. So it's going to take my static route because that's more reliable, because it is based on the administrative distance. And top of that, it looks for the highest prefix length. So example, if I made a static route for 20.0.0.1 like this, and subnet mask is all 255. So the prefix now here is /32. But if you look at here in BGP, it may be learning something like this for 20.0.0.8 and /24. So 32 is higher. So it's going to prefer the most specific route. And it's going to put this route inside the RIB, routing information base. And there is one more table called fib. That's what we saw in the Cisco. They say it is CEF. So I'll tell you why we are discussing this. So based on the CIF, so it is telling this is my attached interface, right, for 12 network. So this is like a buffer. So for all the 12 network, I have to go through this interface. So it is telling that it's all attached. This is all my local network. So here, based on the CEF, this packet is again forwarded to this router 2. Their ARP request happens. And for that ARP request, until it reaches the destination, the ARP continues. Yeah, if it is a different subnet, this is how it happens. So is it in my routing table? No. So I'm going to ARP request and send this ARP request to my default route or the next hop. So once it reaches the next hop, again, it's going to do an ARP request. But what I'm telling is inside your firewall, if you don't know how to reach this, if your routing table doesn't know how to reach your 20 networks, your packet dies here, right? So I don't know how to do an ARP request back. Even if I do an ARP request, I'll not receive an ARP response back until I find it should have
That
something
means,
like at least a default route.
okay, that
to-
means there is missing routing, right? In this case,
I mean,
if I
that's
do,
what I'm telling you. You cannot conclude something like that. I mean, you have to check. As I said, you have to check. Do I have a route from this router? See, logically, if R1 want to reach R3, and if it doesn't know where is R6 is sitting, but I am completely going to rely on my next hop, and this next hop should know where is this 12 network. Otherwise,
exactly.
it should forward this request to the other device. Yeah, it should
Totally.
at least have a static route to this.
Okay.
There, then
Totally.
the ARP request is failing or not is something you have to
Okay.
find. Like that, you have to,
All
you
right.
know,
So,
troubleshoot.
thank
Yeah,
you. Thank you.
yeah, no problem. Yeah. Okay, so let's quickly jump. So is there no further questions? So let me go back to the concept. Yeah.
Hi, sir. I have one doubt. Can you please tell me explain about TTL value? Why the TTL value was decremented from 255 to 254? Could you please explain us?
Because if TTL is decrementing, only then your routing happens, right? I mean, if see, I told you how TTL works, right? Maybe in the study class we discussed how TTL works, right? Do you remember? I mean, what is your understanding about TTL? That would be better for me to understand. As I mean, then I'll be more comfortable to explain you.
As per the diagram, if the packet is traversing from R1 to R4, could you please tell me the TTL value? Is it 254 or 253?
So I told you, right? So if this router has this routing table for 12. So once it reaches here, it has the ARP table. If you look at this, you can see the ARP table here. Where is it? In R2, if I do show IP ARP, so it knows about this destination. So once it reaches here, it's going to decrement this value to 1, and it's telling, okay, you can give it to me and I'll hand over this packet. I know where it is because I know the ARP entry for this. I know the MAC address. So this guy immediately giving the MAC address to this guy, right?
Okay.
With the ARP reply packet. If you see, this is the ARP reply packet we received from R2, right?
Yep. Yes.
Where is that ARP packet exactly? I can figure out where we did an ARP. Where I did an ARP here, I don't see. I mean, we did an ARP right here. We saw in R1, I think. Yeah, that's something I don't know. It's not showing now. So since this device know the MAC address of it for this R2 sends an ARP reply back to R1. R2 sends an ARP reply back to R1. since I know the ARP, I know the destination MAC address, this is just one hop away, because this 10 network is one hop and 12 network is in the other hop, right? So it decremented by one. Within one hop, you can reach me, and I know how to reach this destination because I gave you the MAC address. You give it to me, then this guy is just, since it got an MAC address, it's just forward the packet, right?
Yeah.
Yeah.
Gotcha. Thank you.
Yeah, no problem. So let's jump back to the concept now. The final topic we'll discuss. So let me mute everyone. We'll have a Q&A again. We'll ask questions. Okay, so the next topic is we discussed about layer 1, we discussed about layer 2, we discussed about layer 3, and now we are coming to TCP. Okay. Let me again fire up my whiteboard. Okay. So we discussed this. So very quickly, I'm going here. So this is sender and this is receiver. We are just going to look about the flags today. We got very less time, so we're just going to discuss about flags and nothing else about TCP. The following class will discuss about the other parameters of TCP. So we are just focusing on flags. So I know this is 4-tuple connection. I'm going to write source IP, destination IP, source port SP, and destination port. So only then my packets will be pushed to the other end. And we all know the three-way handshake better now. Send, SYNAC, and for this SYN, it sends an ACK back. We all know this. So the flags. So for all this, you can see your flag, SYN flag, your SYNAC flag been set in both source and destination, right? Both source and destination. All these flags are set. Clear. So what are the other flags? We discussed about the most important, and I would say in the real scenarios we see, apart from this 3 flags, we discussed about the urgent flag. That's something in the traffic generator we cannot do the urgent flag. Let me look for an option, but we can initiate a traffic for push flag. Example, if I said if a multiple traffic is going on here, especially even the, if we will try to establish a HTTP, we can try to establish a HTTP traffic. And the expectation is based on this, the receiver has to, because I mark with push flag from the source, the receiver has to respond back quickly. We are telling that you have to give a priority. In the lab, I saw when I do a HTTP, I saw the push flag coming in for it. Even for telnet, it works. Let's try that. So push flags, and apart from that, topologies and communication functions and protocols of each layer. So we discussed that. So the final thing, okay, layer 4 is something we have to look at, and presentation layer, session layer that's maintained, and what kind of application is used. Okay. So let's do a lab for it. So and I think we covered all the layers. We know the session layer and presentation layer is something we have no control over that. And even if you look at that, we don't see anything here in the Wireshark. We see until layer 4 and the final protocol. What is that? You can see your application protocol, what is being used. So you can see that in your TCP header. So coming back to this, Okay, so let's discuss this push flags. Let's try to generate the push flag now, and we'll see the application used. Together, we'll see layer 7. Okay, so for that, if I show you this show run section HTTP, not there. Show run section HTTP. Okay, so I enable the HTTP. So I enable this HTTP. This kicks in my HTTP application running here in the router. So if I go to router 1 and if I ping R2 show IP interface brief 1201, right? Okay, I can ping. So what I'm going to do simultaneously, let me fire up the Wireshark. Yeah, secure CRT, I'm not interested. Let's open the net 0/1. I can see traffic going in. Okay. So let me try to do a telnet for 12.0.0.1. So what happens here? I'm trying to do a telnet and it is using port 22 and you can see a reset. Okay, that's again, we'll discuss the reset, right? Because that's again a flag. Okay, fine. We got one more scenario here. So I'm going to do a telnet for to push my urgent flag. Sorry, push flag 12.0.0.1 and the port number would be 80. It's open and okay, I keep pressing it. Keep pressing it. Okay, keep pressing it. Okay. So who is marking the push? Source, right? Okay, fine. We got enough traffic here. Let me stop this guy. So going back to the reset. Okay, let's open TCP. So we all know this very well. 4 tuple connection. My who's the source? This guy 12.0.0.1. I try to do, if you see this TCP, my 3-way handshake is not successful because my source IP is this guy, source 12.0.0.1, source port number is 1548, destination is 23. So how do I verify the same thing here? Show TCP brief. I established a TCP connection, but it's not showing me show TCP. TCP statistics. I sent traffic, but why the router is not showing me? Show TCP brief should actually show me show TCP brief. Okay. I think the router 2 should tell us. Yeah. We'll wait. Okay, let it open. Yeah, we'll come back here. So this from the source 10.0.0.1, I try to do a telnet port 23. Yes, I sent a SYN, but I didn't receive a SYN-ACK back. But instead, what I received reset. Why? If you guys know the answer, you can put in the chat. We'll come back to this reset back again. So the 3-way handshake is not successful. You guys use a chat, and if you know the answers, you can tell me. We'll discuss this in Q&A, why we see a reset here. So coming back to this push, if you look at the flags, if you look at this source, this is 10.0.0.1. So I was keep hitting the enter after I opened the telnet session for port 80. So it's telling that to the receiver. So I mark this push packet. You have to send me the application data for HTTP because it's port 80. It's telling to this guy. So now the receiver's responsibility is to send back the packet, and it should give the priority to my HTTP request here. Because I am doing a HTTP request here, and that gives a priority because of this push packet marked here. And we all know this. This thing, if you look at this, I send a SYN, but I haven't received the ACK. But instead, if you go here, all I should see the flag is reset, others reset and acknowledgement set, right? That's basically this an acknowledgement for your SYN ACK. It should be SYN ACK synchronization acknowledged, but instead he's resetting. He's sending an acknowledgement telling that I reset your connection. I am not ready to establish your connection. The answer in the Q&A will discuss. And I want you guys to answer this. And okay, if you look at this, especially we are using port 80, it's not TLS. So we are not doing any kind of TLS handshakes here. So this is not encrypted. And if you compare this different traffic here, okay, this is all related to one traffic. Okay, as we discussed earlier, right? If you look at this stream index, that's the other thing, right? So as I said, for every protocol, the Wireshark is going to maintain a different stream index. So here I am using a telnet. 1 minute, let me erase this. Use my pen. For telnet stream index, I am marking it as SI stream index 0. For HTTP, that's the second stream. So whole different protocol stream index is how much? I think it's 1, right? So that's how it differentiates the traffic. So this is my telnet traffic, and this is my again. This is my, see, if you see the stream index is 1 because this is for port 80. This is totally a different connection. This is a different TCP connection. That's how it distinguishes the connection. The Wireshark does this. And you know, I mean, who is sending this? Keep see for this push. It's sending the push acknowledgement. For who is doing a push? 10.0.0.1 is doing a push. You can see this. It's just sending an acknowledgement here. And if you do, okay, the 7th protocol, what is the protocol we are using it, right? Because for this HTTP GET request, I didn't get a response back because we are not using a GUI to send a HTTP request. Let me check if I see any HTTP traffic going on. There's no HTTP communication happening. I'm just trying to generate a traffic here. You should actually see your, with the GUI, we should see the HTTP request going through. But this proves, right? I mean, I'm talking to HTTP port 80 here. Yeah. Okay. So let me give an unmute permission for everyone. Mute all, allow participants to mute. Yeah, I gave an unmute permission. So Farhana Siraj, so maybe the port 1548 is not open. Okay. HTTP traffic is not yet established. Okay. Port 80 is not open. Okay. The
Sir,
net is not enabled on the receiving side. Yeah, you're
excuse
right.
me.
Yeah.
I have one suggestion here. So, we are having actually we have 4 hours every week, right?
Yeah.
So 2 hours on Saturday and 2 hours on Sunday.
Yeah.
So I'm suggesting here. Can you prepare the lab before we do in the class so we cannot waste sometimes?
If I do that, you will not get the whole picture, right? Why I am doing the lab simultaneously right from the scratch is if I generate a traffic, if I do a testing, if I do everything in place, then you will not understand, right? Makes sense?
No, let's say, I mean, if you have one topology, okay, and we set the subnetting and everything. We set up the IP. We sign in the IP for each devices, and we can make this topology fixed, okay, and we will troubleshoot in this topology. That would be great. This is my suggestion.
Yeah, I mean, let me talk about this internally with my colleagues. Yeah, but I have to discuss this and I'll get back to you. Yeah.
Because we will do all the troubleshooting based on routing and switching, right? There is no more devices.
No, I mean, it's not like that, right? So if you see the topics, even we have IPsec,
Firewall.
firewall, yeah.
Oh yeah, you're right. So let's say we have for now. Let's say we have one topology. I mean, if we have another enough time, even though we know our topology, even if we after the class, we can configure from our side. We can have the same topology and we troubleshoot it from as a practice with ourselves.
No, that happens, what happens there. 1 minute. Sorry for that. Actually, I'm supposed to do one thing.
Because if